Hi! Welcome to my presentation on semantic slicing of software version histories. It's a paper by Professor Yi Li, Professor Julia Rubin, and Professor Marsha Cecek. And it's a presentation by me, Sai Saudat. Let's begin. So the problem here is that cherry picking is hard. However, it's everywhere. What's cherry picking? Cherry picking or backporting is a mechanism in SCM, software configuration management systems, where we take a change that we did on another branch, we take it and we apply it to a different branch, maybe our main branch. It can be a feature or it can be a bug fix. I have personally used it a lot when I was working as a software engineer. We use this mechanism to import only the important commits from our feature branches into our main or production branches. And it can cause a lot of bugs. This is how we can do it using the command line. And yeah, there's a problem with this. Cherry picking only understands temporal and text level changes or dependencies. But a lot of times we are looking for functionalities, we're looking for semantics. For example, in a feature branch, we might be working on a certain feature. And we don't want the formatting commits or empty commits or reverts. But SCMs won't understand that. They don't understand what's a functional commit, what's a semantic commit, and what is just a formatting one. The developers have to do it manually, and doing stuff manually is the worst. Here comes CSlicer. What we have here is a history of our program from P0 through PK. Each version of this program is a valid program, meaning it follows the syntax rules of a valid programming language. In this paper, featherweight Java has been picked, which is a simpler version than Java. In our history, which is represented by H, as I said, we have different versions of the program. We start by P0 and we apply change sets represented by delta. And we go to P1, P2, all the way through PK. As I said, we're looking for a certain functionality and we use test cases to define that functionality. Test cases are represented here by T. So we say that if PK has our desired functionality, then it has to pass all the test cases defined in T. CSlicer is supposed to deliver H prime, which is a subhistory of the original history. We expect the H prime to be applied to P0 and deliver a valid program. It should still be well typed and it should pass all the tests. Okay, so how? The brute force version is to just try every combination of the commits, which will give us 2 to the power of k different programs. And for 20 commits, 1 minute for each compilation, we will have 2 years. So that's not really an option. As a matter of fact, the optimal solution is proved to be NP complete. It cannot be computed in polynomial time. That's why the authors suggest that we settle for a suboptimal option. It basically will use the final version and try to go back and drop every commit that isn't necessary for our functionality. How does it work though? Okay, it has 2 phases. The first phase is semantic slicing. This, for example, is our foo.java file. It's a simple Java file with 2 classes. And right here, we have its history. Another way of looking at this file is through an abstract syntax tree, or an AST for short, which represents the classes and its methods and fields. Let's say in this file, we are looking for the functionality of boo.boo2 returning -1. As you can clearly see here, we don't really need the parts that have been opaqued here, like this part. A comment doesn't really do anything semantically, or this like function boo1, it's not even run during this test. We're only running boo.boo2. So if we delete this, or more importantly, if we leave the commits that add these lines out, then we will still have our functionality and we will get rid of the extra weight. Okay, let's define some stuff. First, we're going to define functional sets. A functional set is a set of elements that is directly executed or used while executing our test sets. In our example, boo.boo2 and bar.bar1 are in our functional set. They are directly used. Next, we have our compilation set, which are elements that are referenced by the functional set. These elements are important for a compilation to be successful. They can include enclosing classes or referenced fields. In our example, we have classes boo and bar and the field boo.b. Their implementation doesn't really matter, doesn't really change the way our tests work. But they must be present while we're compiling our program and we're running our tests. Okay, so CSlicer, which is the core components, it will go through the chosen history. It will iterate backward from the latest change to the first change set. It will only collect the changes that are required to preserve the behavior of the functional and compilation sets. For each change set that CSlicer goes through, it will divide that change set into a bunch of atomic changes. Now, what are atomic changes? They are changes that, they update our AST. How do they do that? It's either in the form of an insert, in the form of a delete, or in the form of an update. Okay, so it will turn each change set into a set of atomic changes, and then filters that atomic change set into so that it gets the atomic changes that are important to us. So we will get our delta prime I, which can be empty. For each atomic change, if it's an insertion and it's inside the compilation set or the functional set, it will be included. If it's an update and it's inside the functional sets, it's included. Otherwise, we want nothing to do with it. There's a corner case though. In featherweight Java, subtyping and casts are still allowed, and they can affect the method lookup function. So, if the atomic change changes the method lookup function, it will be automatically included, even if it has nothing to do with the compilation or functional set. And here's a pseudocode of how this filtration system works. So to recap, we have our test cases and we have our program history. From our program history, we get the final version, we run the tests, and using the funcdep function, we get our functional set. Then, using that functional set, we get our compilation dependencies, which is computed using all these rules. Finally, the slicer component will get these sets along with the version history, and it will deliver our H prime. We will apply this H prime to the initial version of the program, so we can get the program that we want, which only has the required functionality on top of P0. So far, we analyzed our program. We understood which functionalities and which semantic changes need to be included in our subhistory. But the problem is that SCMs don't really understand functionality or semantics. They understand text. They understand text dependencies, hunks, and contexts. Okay, so let's first briefly talk about how commits work. If you have a file like this, and we want to go to this I just added 2 lines, and we can see those added lines using the diff command in the command line. You will understand that the added part is called hunk, and the lines surrounding it are called context. So the important part for us is the hunk. However, the SCM needs to see the context, needs to use unchanged lines so that it can understand where the hunk is supposed to be applied. So we go from our phase 1 with ASTs, change sets, and atomic changes to our phase 2 with hunks, context, and textual commits. But how? Okay, so one way is that we use RH prime. We will get the corresponding commits for each delta prime if it's not empty. We will keep the corresponding commits included in RH prime. Easy. However, that will lead to a bunch of errors. Why? Because each commit has some changes that we want and some changes that we don't want. And those changes that we don't want have consequences. They might be using stuff that were defined in previous commits that weren't included. So instead, we will find the changes that aren't inside the compilation sets, and we will revert them back to how they were in the P0 version. In the final commit, like we will get our sub-history and we will add a final commit that reverts all these unwanted changes. Then we can map all the atomic changes into hunks, which are the textual changes. And finally, we have to make sure we don't have any hunk conflicts. Okay, to define what these are, we have to first define hunk dependencies. We will say that a change set delta I is directly hunk dependent on delta J if and only if delta J contributes to either delta I's hunk or its context. Meaning, if we try to apply delta I before or without applying delta J, we will face a conflict. The SCM won't know how to apply delta I because the context or the hunks won't match. So we have hunkdip function, which will calculate all direct and transitive dependencies of hunks. This is like the pseudocode of how this procedure works. It's a recursive function. And once we find all the dependencies, we will know what hunks need to be included in the subhistory so that we can avoid conflicts, hunk conflicts particularly. And that's how this solution isn't optimal, because we will have to include some changes that weren't contributing to the functionality, but were needed for the program to be compiled. So that's pretty much it. Finally, we have a bunch of final tweaks, like non-Java files are ignored by default unless told otherwise. And the user can mark specific files to be included or excluded based on their domain knowledge. It can optimize the solution. All right, let's go to evaluation. How good is it? I'll keep this part brief. Evaluation has been done on 3 projects: Apache Hadoop, Elasticsearch, and CSlicer itself. How meta. On Apache Hadoop, 91 commits have been found by CSlicer out of a history with 267 commits, which gives us a 66% reduction. So, similar thing for Elasticsearch with 67% reduction, but Elasticsearch had 13 false positive, meaning that out of those 17 commits that were found by CSlicer, only 4 of them were actually crucial. And for CSlicer, similar results, we got a 60% reduction, but it's been mentioned that CSlicer wasn't as well managed as the other 2 projects. Like, the commits weren't as strict as the other projects. The second part of the evaluation is about its applicability. They want to see how efficient is it and what's its history reduction rates. So for this evaluation, they added Project Maven on top of the other 3 projects. From each project, they chose 3 functionalities: a feature, an enhancement, and a bug fix. For each feature, they chose histories of size 50, 100, and 150 commits. And they produced these results here. I'm not gonna spend too much time on this. For each feature, for each project, for different history sizes, you can see the reduction rate and the times. The times are like basically not a problem. It's only run once, so even if it takes a long time, it doesn't really matter. And the reduction rates are amazing. So yeah, we can confidently say that this tool works. We can trust it to like get rid of unwanted commits while cherry picking. And now for my thoughts. First, the feature definition depends on tests. I see that it's a fair assumption. However, it puts a dent on its usability. I have worked as a software engineer for 3 years, and I can confidently say, at least in Iran, well, we don't really care about tests. I know it's a bad thing, it's a best practice, we have to use tests, and like, this assumption works great for like test-driven development projects. But if, like it's been mentioned in the paper as well, if the tests aren't well defined, like it happened on Elasticsearch as well in the evaluation. That's why it had like 13 false positives. And yet, if the tests aren't well defined, if they aren't like, specifically targeting the parts that are like related to the functionality that we want, then it won't fail, but like it might not work as good. So like maybe we can find other way to define our desired functionality. Okay, the second one is that all delete atomic changes are ignored, which will definitely produce a lot of dead code. So for example, we might want to use this functionality to import our desired changes from feature branches into the production branch. And we definitely don't want a lot of dead code on our production branch. So that's why it might cause a lot of problem. I actually have a solution for this. Maybe after everything is done, we add a final commit, removing all the dead code using a dynamic analysis. So we have to mark every atomic delete change. And after everything is done, we run the project one last time, and if those deletes that were in the compilation set didn't run in the final version, we can safely say that it was dead code, we didn't need it, and we get rid of it. Okay, the third suggestion is that it's 2024, practically not using LLMs is considered illegal. So maybe we can train a classifier, like not LLM, just the classifier, and we can show each commit, each hunk, or each like change sets to it, and it can label it for us. It can just with a simple Boolean response, it can confirm that this commit is related to our functionality, or if it isn't, as an alternative like method. The fourth suggestion is that it's mentioned as a limit in the paper that we can be sure that this CSlicer would work on every project, since they only tested it on 4 different projects, and they said that it would take too much time, it wasn't feasible for them to test on more projects. However, if we add a final step, when after everything is done, we apply the sub-history changes to the initial version, we get our program, and we run it one last time. And we run it one last time, we run all the tests and see if they passed. If they pass, we can safely say that, yeah, it worked, there were no compilation errors, it has the functionality, and everything is fine. So this can be a way of automating these tests. And finally, this is more of a concern, is that why isn't this a thing yet? I said this already, this is a pain point for me. Like, I have done this, I have stayed up all night cherry picking all my commits for production. So yeah, it is a pain point for me. I understand the impact of this research. So my concern is, why hasn't this been applied anywhere? Coincidentally, I ran into the Gitpuddler project last week while I was researching for this presentation, and it's a rather new project. It's done by one of GitHub's co-founders. They are trying to take the guesswork out of like using branches for different features. So I think they can align somehow. This might be a good thing. This might be a good collaboration. Maybe reach out. Yeah, so those were my thoughts, and that was my presentation. Thank you for your attention. I hope you enjoyed it. I hope I managed to deliver on my promises on my presentation skills. And yeah, thank you for your time. I am waiting for your response. I hope you like this.